Hello, Astronomy. Mr. Janowski here. Has promised after we go through some slides, I'm going to go back afterwards and do a quick version and put it up on YouTube so that if you miss the material, you can get it that way. Or if at the end of the chapter you want to review it, then there it is. So let's get started with the first one of these videos from the first set of slides. So started off with the homework stuff. Yeah, if you haven't done this yet, please do the signature page of the syllabus, the student information form, and your learning style, and tell me what letter or letters that you are. V for visual, A for auditory, and K for tactile kinesthetic. And then we talked about the learning styles real briefly. I'm not going to go over this again. The idea is that if you know your learning style, there might be certain things you can do that will make studying a little bit easier for you. So then we looked at this in the very first day. On the very first day, we looked at this on Dark Site Finder. So this is a website that shows you how good the viewing at night is in different places. So on this map, dark is good, bright is bad. So the whole eastern part of the U.S. is almost completely a pretty crappy place to look at the stars. Western part of the U.S., it's much better until you get to California and Washington and Oregon and such. Canada is much better for the most part. And if we zoom in on our area here, so here we are. This little red point here is Bethlehem. Yeah, ABE. There's not really a good place in any of those towns to look at the stars. In fact, where we are, you have to go pretty far out to get to even decent astronomical viewing. Some places are better than others, but there's just too much light pollution where we are. So obviously, we're better off than New York or Philadelphia. Those are terrible places to go to look at the stars. But yeah, even where we are, it's not very good. And I've said this a few times, but it's still true. Remember that human beings as a species for almost the entire time, for about 200,000 years, when you go out at night, if it's a clear night and there aren't any clouds, you could have seen thousands of stars on any given night. And you could have seen the Milky Way galaxy. And it was just a huge part of what it meant to be a human. That was part of our daily experience. And it was like that for 200,000 years or so. And then in the last 150 years, we started ruining everything with light pollution. So, yeah, light pollution bad. Some kinds of streetlights are better than others. If you have to have a streetlight to keep people from getting murdered at night, to keep the sidewalk safe, to keep the street safe for driving, have this kind that throws the light down. Don't have this kind that throws the light all the way up into the atmosphere, which just ruins the night sky for everyone. And again, I talked briefly how, near these sandy beaches where sea turtles live, where the mommy sea turtle lays her eggs. When they all hatch, the sea turtles are supposed to make a mad dash down to the water so they don't get eaten by a seagull. But the problem is, if they happen to hatch at night and there's bright lights behind them, their instincts get all messed up. They get all confused. And instead of heading towards the ocean, they head towards the streetlights. They head towards the town. And that's not a good place for a baby sea turtle to be. So, yeah, light pollution. It's not good. So here we go. Chapter 1, Cycles of the Sky. So I am less than 4 meters away from you right now. That would be true if we were in room 321. If I'm at the front of the room, even if you're in the very back row, you wouldn't have been more than 4 meter sticks away. The thing is, even the very nearest star, Proxima Centauri, which is this guy here, it's 4 times 10 to the 16th meters away. It is 10,000 times further away than the teacher at the front of the room would be. Now, the farthest naked eye star, meaning the farthest away star that you can see without having a telescope or binoculars or something like that, is a star with a rather boring name, V762 Cass, which is a star in Cassiopeia. And this star is about 4,000 times further away than Proxima Centauri. They're not at all related to each other. They're not near each other in the sky. But the thing is, the point of this slide is that all of the stars are so far away that you can't get any kind of sense of their three-dimensional arrangement when you look at them. They all just look really far. You don't get a sense of the depth. Now, maybe you kind of can. It looks like, this star here is in front of these stars in the background. Um, but you can't even actually tell that for sure. Um, yeah. You don't get a sense of the 3D arrangement of the stars. I'm going too slow. I'm going to pick up the pace a little bit. So, we use this idea of the celestial sphere. The celestial sphere is just a model. This is not actually what's happening. Um, However, it's a useful way of describing the observations we see. And according to this model, you imagine that the Earth is fixed in space. So right away, dead wrong. The Earth is not fixed. The Earth going around the sun. The sun's going around the center of the Milky Way galaxy. The galaxy's spinning. The galaxy's doing other things. There's a whole lot of things going on. But for the sake of this model, you picture it as the Earth is just dead center in the middle of this giant sphere. And instead of imagining all of the stars where they actually are in three-dimensional space, you picture them all as existing on this big sphere called the celestial sphere that is just some big distance away. So if we're looking at the star in this image that's going straight up, the star is way, way far away, but we just say, okay, that star, it's on the celestial sphere. It's right here. And this star over here, that's not as far away in reality, we still say, well, that's on the celestial sphere too. So we just imagine that they're all the same distance away. And again, this is not an accurate description of what's really happening, but this is a very useful way of describing the observations that we make. So it's a model, it's wrong. There's a quote that we in science like, that all models are wrong, but some of them are useful. That's true of this. This model is not wrong, this model is not right, but it is very useful. And what I said here, okay, at the very bottom, if you were some distance away from the Earth, but still within the celestial sphere and far from the edge, you would see the entire sphere. So what that means is, if you were not standing here on the Earth, but if you were up here, if you were, imagine, halfway to the celestial sphere, you could look all around you in every direction, and you would see almost all of the stars. If you look back towards Earth, the Earth would block some of your view, but you would still see most of the stars. So if you were away from the Earth, you would see all of the stars on the celestial sphere. However, we're not usually away from the Earth. We're usually standing on the ground. And what that means is the ground is going to block half of our view of the sphere. So this sphere, it goes all the way around. There are stars down here. We imagine them, they're way out here, but we imagine them being on the celestial sphere. But when you're standing on the ground, you can't see it. So here we've got a little shepherd with his staff and a little doggy and 3 little sheep. So they're hanging out there. But yeah, if you're standing on the Earth, you can't see the whole thing because the ground blocks your view. So we have a vocab term, the horizon. This is a word you probably know already. The horizon is where the sky meets the ground. So you can see stars above the horizon. You can't see the stars below the horizon because the ground is in the way. So which stars you can actually see is going to depend on a couple of things. One of them is your position on the Earth. So depending where you are, north or south, you're going to be able to see different stars, and the ground is going to block different stars from you. The other thing that affects this is the Earth's position in its orbit around the sun. So there are some stars that you can see all year round. Where we live in Pennsylvania, any clear night, you can see the North Star, and you can always see the Big Dipper. But there are other stars that you can only see from here in Pennsylvania during certain times of the year. Orion being one of them. Orion is not always up, but Orion comes up in the fall, and if you know to look for it, it's one of the things that lets you know, oh yeah, winter's coming. A calendar would also work for that purpose, of course. So then I asked this question, what is this? So you're probably looking at that and you're saying, oh yeah, that's a face. Well, it's not a face. It's just a bunch of stars. Humans have pattern-seeking brains. Whenever we see anything, our brains are just wired to naturally try to put it together and see something, even if that thing is not there. That is just how our brains work. There's a name for this. You don't need to know the name for this. This is, astronomy. This is not psychology or wherever you would do this, cognitive science. But there's a term, pareidolia. This is the tendency that everyone has to interpret vague stimuli as something that you already know. So, for example, this weird random shape here, that is the elephant's ear, if you're looking at it, yeah, you can probably see a face there. I don't think I even need to point this out. There's the eyes, there's the nose, there's the mouth. Yeah, this is a really well drawn face. And I'm not sure. I almost don't believe this picture. This looks like a Photoshop job. But I don't know this elephant personally, so I can't attest to it either way. But yeah, the key is we have pattern seeking brains. So, with that idea of pattern seeking brains, thousands of years ago, people would look up at the stars and they would see these different patterns up in the stars, and they would use their pattern seeking brains and they would find patterns in them. What they would find are called constellations. So, the root of the word constellation, con means with, and stella means star. That's how we get constellation. Um, Yeah, people look up at the stars, they see this pattern, and somebody saw this pattern, convinced themselves that they saw a lion, and then convinced everybody else that they saw a lion. And they looked at this pattern that looks like a cross or a T or a sword going this way. I mean, you can convince yourself that it looks like lots of things. Uh, they convinced themselves that it looks like a bird. I don't know if Cygnus is a swan or a goose or what, but yeah, they saw this and they're like, oh, yeah, that's a bird. Um, Vaguely, it's a bird, but it's not really a bird. Without all these lines, you're not going to really see the bird like that. But the key is, thousands and thousands of years ago, people saw these things, they saw patterns in them, and they gave them names, and they attached the things they saw to their own mythology, or vice versa. They used their own mythology and attached it to the patterns they saw. And so the ones we use most often are kinds of the ones in the Western tradition. So most of the constellations we're going to have are going to have their mythologies based in ancient Greece and ancient Rome and things like that. And other cultures from different parts of the world, they would see the same pattern, and maybe they didn't see a lion. Maybe they saw something else and it was going the other direction, and they would attach it to their own stories and give it its own name. So, yeah, that's what constellations are. They're just vague patterns that somebody thought looked like a shape, so they gave it a name. So, important point here, something to remember about constellations is that think back to the celestial sphere. When you look up in some direction, the best example here is really going to be these two stars, this guy here and this guy here. And notice that they're not particularly close to each other, and they're not at all the same distance from Earth. But when you look at them from Earth, because they're in the same direction, they look like they're right next to each other. Because again, using the celestial sphere model, we don't have any sense of the actual distances to things. So the fact that they happen to be in the same direction means that they look like they're right next to each other. So an important idea here is that in a constellation, if you see two stars that seem to be near each other, the only thing you know for sure is that they're in about the same direction from Earth. They might actually be near each other in space, but they could be very different distances away in space. And kind of to a different point, if you weren't on Earth, if you were on some other planet way far away and not even in the same solar system, you'd have to be on some way different star somewhere far away. But if you were over here, I'm not even sure that you guys can see the cursor when I do these things on Screencastify. But if you were somewhere else and you looked at those same two stars, then on Earth they look like they're right next to each other. If your planet was over here, those stars have nothing to do with each other. They're not at all related to each other. Same deal here. If I look at, I guess, the haunches of the lion here and his shoulder, I don't know what's going on here. These guys seem like they're kind of near each other. One of them could be twice as far away, or 10 times as far away, or 100 times as far away from the other. And they really have nothing to do with each other in three-dimensional space. But from where we're observing them, they're in about the same direction. So we say that they're right next to each other, even though that's not necessarily true. The other thing, this is called proper motion. The stars are actually moving relative to each other. Stars are moving all the time, and they're moving very quickly, thousands or tens of thousands or even hundreds of thousands of kilometers per second. These things can move very, very quickly. But from Earth, they don't seem to move relative to each other very much. Now, over the course of the night, we'll get to this in the next bit of slides, the stars seem to move across the sky, but they move all together and they move locked in space compared to each other. But the constellation itself that someone saw thousands of years ago and thought this one looked like a lion, if you brought that person from 5,000 years ago to today, 2020, well, they'd be in for a big surprise in lots of ways. But if they looked up in the sky and they saw these things and they weren't too annoyed that we had ruined the night sky with light pollution, but if they saw these stars, they would be in almost exactly the same place that they were 5,000 years ago. So these stars may have moved, like in this image, a pixel or two, one way or the other. Even though they're moving very fast, they don't appear to move relative to each other, even over very big periods of time. We can actually measure it, but it's not something you're going to see with your naked eye. So, yeah, that's weird. So, how many constellations are there? It turns out that there are 88 official constellations. For some reason, it's just an easy number to remember, 88. What that really means from an astronomer's point of view is because the constellations, all the stars stay fixed over time relative to each other, apparently from Earth, and the constellations all stay in the same positions relative to each other, too, you can use the constellations to kind of make a map of the sky. So if I'm looking up here, I can. The text is really tiny on my screen. I think this is Libra. Okay, here's Ursa Minor. I can't read them. The text is really tiny. Yeah, but anyhow, how would an astronomer actually use the constellations? The astronomer might, say to the other astronomer, "Yeah, I'm studying, a cluster of stars in Ursa Minor." Now, what they mean when they say that is not that these stars are actually officially a part of Ursa Minor. It just means that they're in that direction. They're in that same neighborhood. So the sky is kind of divided up into 88 different irregular shapes. And if the area you're looking at is near a particular constellation, you would say that it's in that constellation. So that's how that works. But again, the names of the stars and the names of the constellations, not really important. Astronomers don't necessarily know the night sky very well. So if you go out at night and the stars a little bit, you might go, "Oh, that's Orion, that's the Big Dipper, that's Polaris, that's the Pleiades. There's Cassiopeia." Those are kind of the big ones that we know. And an astronomer would know those. Those are the common ones, but they're not going to know all of them, and they don't know all of the stories. That's not what astronomers do. And that's as far as we got. Because I had planned out to get a little bit further in a certain number of slides and everything, and I had some nice review slides at the end, but we didn't get that far, and that's cool. I don't mind that at all. So we stopped there after the first slides, and next time we'll pick it up. We'll talk more about the daily motions of the stars, and then we'll talk about the yearly annual motions of the stars. So hopefully this helps.